we are going to do a question in the Year 12 Maths Methods VCAA VCE official exam paper for the year 2016 exam 2 in section B, the extended response section. Now, if you go to the exam report, from the exam report, you can work out the average mark for each one of the 4 extended response questions that existed in this exam. You would see that the average mark for question 1 was 53.6%. The average mark for question 2 was 56.7%. And the average mark for question 3 was 51.3%. And the average mark for question 4 was 29.5%. The average mark for the whole of the extended response section was 45.2%, which was a failure. But normally in the extended response section, year after year, the average mark tends to be anywhere from 40% to about 55%. So if we assume that the most difficult extended response question was the question with the lowest average mark, then it would be question 4 with 29.5%. Now, which was close to half of the average mark for the other 3 questions. So we can debatably say that the most difficult extended response question was question 4, and as a result, we're going to go through the worked out solutions for question 4. Now, question 4 was the following. A, express 2x plus 1 over x plus 2 in the form a plus b on x plus 2, where a and b are non-zero integers. Well, basically, if you were doing such a question by hand, you would need to use long division, and you would say 2x plus 1 divided by x plus 2, and so forth. But of course, because it's exam 2, where you can use a CAS calculator, it's much quicker and easier to do the long division on the CAS calculator. And if you like, you can use improper fractions function on the CAS calculator, and you will get the final result as being 2 minus 3 on x plus 2. But for those of you that would like to have a little bit of practice in regards to doing this by hand, just in case such a question appears in exam 1 where you can't use a CAS calculator, then which does happen from time to time, then the way you work it out is to say the following. We've got to work out 2x plus 1 divided by x plus 2. So you say 2x plus 1 divided by x plus 2. 2x divided by x is 2. Then you say 2 times all that. 2 times x is 2x. 2 times 2 is 4. Then you put the little red horizontal line, and you put a minus, and you work out that minus that. What's 2x minus 2x? It's 0. And what's 1 minus 4? Nearly 3. That's a remainder. So the final answer will be quotient 2, remainder negative 3 divided by x plus 2. So that's part A done. Now we go to part B. What is part B about? What is part B about? Part B. Let F, where the domain is a set of real numbers except x equals -2, where f equals 2x plus 1 divided by x plus 2. B part 1. Find the rule and domain of the inverse function of f. I repeat, B part 1. Find the rule and domain of the inverse function of f. Okay, well, basically here, in a few words, they want you to find the inverse function. But because they want you to work out the domain, it's a good idea to work out the range of the original function. And the best way to do that is to graph it on the CAS calculator, of course. Here we know that fx equals 2x plus 1 on x plus 2, which, like we saw, came out to 2 minus 3 on x plus 2. And if you put the main function at the front, then you can see that it's a hyperbola with vertical asymptote at x equals -2 and a horizontal asymptote at y equals 2. Now, because it's got a negative, it's going to be a negative hyperbola, so the arm will be here and the second arm will be there. From the graph that we can see on the piece of paper here, and from the graph that you would see on your CAS calculator, you will see that the range will be the set of real numbers except y equals 2, because there's a horizontal asymptote there. So therefore, from that information there, we can go on and say that the original function, which is -3 on x plus 2 plus 2, has got a domain equal to the set of real numbers except -2 as stated in the question, and it's got a range of y element of real numbers except y equals 2. Now, from that, we can now find the inverse. Like you should know, to find the inverse, you need to interchange all the x and y's. So therefore, wherever there's a y, you put an x. Wherever there's an x, you put a y. Again, wherever there's an x, you put a y. And wherever there's a y, you put an x. So when we say that to find the inverse, you got to interchange all the x and y's, we mean you got to interchange all the x and y's. Now, then you got to get y by itself. So you get y by itself here. So you put the 2 over there, and then you can multiply both sides by y plus 2, and then divide both sides by x minus 2, and then get y by itself by putting the plus 2 on the other side, which becomes minus 2. And you got an y by itself. And therefore, the inverse function is equal to -3 on x minus 2 minus 2, where the domain of the inverse function is set of real numbers except 2. So that's part B, part 1, done. Now we go on to B, part 2. What is B, part 2 about? Well, question 4, B, part 2. Part of the graphs of f and y equal to x are shown in the diagram below. All right, that's the f graph, which is what we have been doing, and that's the line y equals x, which of course, cuts the first quadrant in half at 45 degrees. So repeat, part of the graphs of f and y equals x are shown in a diagram below. Find the area of the shaded region shown in the diagram. So you've got to find the shaded region between the f curve and the curve y equals x. You've got to find that shaded region there. How do you do it? Well, you basically do it by using integration. Find the area on the CAS calculator. You can find the that shade area on the CAS calculator. Okay. And again, just in case such a question would appear in exam 1, which it does, it's not a bad idea to do this question a bit by hand. So, like you know, the area of the shaded region equals integral of the top curve minus the bottom curve. So therefore, that's equal to the integral of the top curve. The top curve here is f, and the equation of f, like we saw before, was -3 on x plus 2 plus 2, minus the bottom curve. The bottom curve is that straight line, y equals x, so it's minus x dx. Now, to work out this by hand, you've got to find the intersection point here, and you've got to find the intersection point between the curve and the line here. So you've got to find x1, x2. How do you do it? Well, find x1, x2, that is, find the intersection points of the curve and the line using CAS calculator or by hand. So, you're going to put fx equal to x. So fx, which is -3 on x plus 2 plus 2, we've seen that a couple of times, and that's equal to x. And then you can find x using the solve function on the CAS calculator or by hand. So please, in the exam, please use the solve function as much as possible. So find x using the solve function. But just in case this question appeared in exam 1 where you can't use the calculator, how would you do it by hand? Well, you would put the plus 2 on the other side, multiply both sides by x plus 2, and that gets you to -3, x plus 2, x minus 2, difference of 2 squares, x squared minus 4, and then put the -4 on the other side, becomes plus 4, and becomes 1 equals x squared, and therefore square root, then get rid of that square by saying opposite square, it's a positive negative square root, and it gets you to x equals plus or minus 1. So now we know that that intersection point there is -1, and that other intersection point there occurs at +1. Now, so therefore, the area of the shaded region is equal to the integral of the top curve, which was -3 on x plus 2 plus 2 minus x dx. And now we know what x1, x2 are. The lower limit is x equal to 1, and the upper limit is x equals 1. So, and then you can put that into the CAS calculator and it will give you that. That shaded region there is equal to -3 log e 3 plus 4 units squared. Now we move on to the next part. The next part is question 4b, part 3. Part of the graphs of f and inverse f are shown in the diagram below. So you got the original f curve that we've been investigating in this question so far, and and the inverse f is this curve here. Remember, one way in which you can find the inverse is to reflect the curve into the line y equals x. And you can see the line y equals x through there. And if you reflect the f curve into the line y equals x, you will get that inverse f curve there. Now, they show a shaded area between the original f curve and the inverse f curve. Find the area of the shaded region. They want you to find that shaded region there. How do you do it? In the quickest possible way. Well, you got to realize that like I've just been saying, that's the x-axis, y-axis. If you drew in the f curve, and then you draw in y equals x line, then of course one way in which you can find the inverse is to reflect the original f curve into the line y equals x. So if you reflect that point on the f curve, sorry, I've got something in my mouth. If you reflect that point on the original f curve into the line y equals x, you will get that green point there. That's one point on the inverse. If you reflect that point on the original f curve in the line y equals x, you're going to get that green point there, and so forth and so forth. And you eventually get that green curve there, which is the inverse f curve. Now, we know that based on what we've been saying, that distance there would have to be the same as that distance there, based on what we've been saying. So therefore, in the previous part, when you think about it, in the previous part, question 4b part 2, they wanted us to work out that black shade area there. Now they want us to work out all of this shaded area there. Well, based on what we've been saying, that to get the inverse curve, you have to reflect in the line y equals x, then clearly that distance there will be the same as that distance there, and clearly that green area would have to be the same as that black area there. So as a result of all that, that whole shaded area, which is what the question wants you to work out, will be twice the black area. In other words, all that shaded area there is equal to twice the answer that we got in question 4b part 2. And by realizing that, you get the question out relatively quickly. This question wants you to find the total shaded area shown above. Okay, and like I say here, the area of the black shaded area plus the area of the green shaded area. So therefore, based on what I've been saying, the total shaded area, which is what the question wants you to work out, is equal to 2 times area of the shaded black area, which we worked out in question 4b part 2. And like I've been saying, because the inverse function is a reflection of the original function into the line y equals x, then it will be 2 times the answer that we got in question 4b part 2. And that comes at the 2 times -3, -6, 2 times 4, 8. So the final answer comes at the -3 log e plus 8 units squared. Now we go to section 4c. Now, what is section 4c about? Section 4c is about this. Part of the graph of f is shown in the diagram below, where there's a point on f which they call P and it's CD. the point P, CD is on the graph of F. Find the exact values of C and D such that the distance of this point to the origin is a minimum. And find this minimum distance. I repeat, the point PCD is on the graph of F. Find the exact values of C and D such that the distance of this point to the origin is a minimum. And find this minimum distance. How do you do it? Well, the question is dealing with the F curve. On that F curve, there's a point CD. And they want us to find the point CD where the distance from CD to the origin has got a minimum distance. How do you do it? Well, because they want you to find the minimum distance, then there's a good chance we got to use the distance formula. And that's what I did here. The distance formula, which is the distance from point A to point B, is equal to square root of x2 minus x1 all squared plus y2 minus y1 all squared. So therefore, that's the point P, which I call here point A, which is CD, is x1, y1, and the origin, which I call here green B, is 0, 0, which is x2, y2. So all we're going to do is just to sub in the values. So therefore, what's x2? x2 is 0 minus x1 is C all squared plus y2 is 0 minus y1 is D all squared. And then that boils down to 0 minus C negative C all squared is C squared plus 0 minus D is negative D all squared. So negative D all squared comes out to D squared. So that's the distance AB. Now, so yeah, by using the distance formula, we have worked out the distance from A to B, or as they say in the question, from P to the origin is square root of C squared plus D squared. But the problem with this is that to find the minimum distance, we got to have this in terms of two variables. But unfortunately, this is at the present time in terms of, I repeat, that was a little mistake. The thing is this, to find the minimum distance from A to B, we got to reduce these two variables, C and D, to one variable. How do you reduce these two? How can you reduce two variables to one variable? By doing the following approach. Here we have two variables, and as a result, we have a problem, like what I just said. We reduce these two variables to one variable by using the graph equation. And we do that by putting x equals C into the graph equation. Because by putting x equals C in the graph equation, we'll find the corresponding D variable. So we put x equals to C into the F curve equation, and D is equal to negative 3 on x equals C plus 2 plus 2. So now we know that when x equals C, D is equal to negative 3 C plus 2 plus 2. So therefore, like we saw earlier on, the distance from A to B is equal to the square root of C squared plus D squared, and that's equal to C squared plus, what's D? We just saw that D is equal to negative 3 on C plus 2 or squared. And at which point we have got now the distance formula from A to B, or as they say in the question, from P to the origin in terms of just one variable, which is C. And we can now find that variable C. Minimize this by using CAS calculator. Graph this on the CAS calculator. So we can now find the minimum distance by graphing this distance formula there. Now, when you graph the distance formula AB, which is stats, on the CAS calculator, you're going to get a graph like this on the CAS calculator. Remember, we are graphing the distance from A to B, or as they say in the question, distance P to the origin, which is distance AB, against C. Now, the minimum distance between A and B will occur there, at that point there. And then on the CAS calculator, you can find the minimum distance by using the minimum function, and it comes at the C. It comes at the C equals -0.268, and when that happens, the minimum distance between A and B is 0.379. And so, like I said here, find minimum coordinates on CAS calculator. We've done that. And the minimum distance from P to origin is 0.379 units. Now, we now know the value of C that occurs when we have got the minimum distance between A and B, or as they say in the exam, from point P to the origin. Now we're going to find the corresponding D ordinate. Well, to find D, put C equal to 0.268 into the D formula we got before, which was D equal to E3, C plus 2 plus 2. So therefore, D is equal to E3, C is 0.268 plus 2 plus 2. And when you put that into the calculator, it comes out to the follow. It comes out to a number, which I haven't got here, but you will get a number, and you get the answer. So question 4C has been done. Now we go to question 4D. What is question 4D about? Question 4D says the following. Let G, where the domain is between -k infinity, where G is equal to kx plus 1 on x plus k, where k is greater than 1. Show that x1 less than x subscript 2 implies that gx1 is less than gx2, where x1 element between -k infinity and x2 is element between -k and infinity. From the exam report, you could see that many students found question D a bit difficult. How do you do question D? Well, you take the following approach. We know that fx equals 2x plus 1 on x plus 2. And when we graph that, we get vertical asymptote at -2 and horizontal asymptote at y equals 2. Here in this question 4D, they tend to give you a more general form of the same equation. Instead of having 2's, they replace the 2's with k. And as a result, you get gx equals kx plus 1 on x plus k. So therefore, from that, we can replace the 2's with k's and get a graph as shown here, where the vertical asymptote is at x equals negative k, and the horizontal asymptote is at y equals k. Now, in the question, they refer to x1 less than x2. So we can say that x1 is less than x2. And they say in the question that x1 is between negative k and infinity, which is consistent with my diagram, that x1 is between negative k and infinity. And they say in the question that x2 is between negative k and infinity. And x2 is between negative k and infinity. That's also consistent with the question. Now, they go on to say this in the question, that they're saying that if x1 is less than x2, you've got to show mathematically that gx1 is less than gx2. Well, you can see from my diagram that if that's x1, the corresponding gx1 will be that. And if that's x2, you can see from my diagram that the corresponding gx2 will be that. And they want you to prove mathematically that, that gx1 is less than gx2. I mean, from the graph, you can see very clearly that that is the case. From the graph, you can see very clearly that gx1 is less than gx2. But in the question, they want you to prove that mathematically. How do you prove that mathematically? Well, by taking the following approach. That when you think about it, all along here, the curve has got a positive gradient. So when you think about it, the way the question is set up, you can see that for gx1 to be less than gx2, there has to be always a positive gradient. So to prove that gx1 is always less than gx2 in this section, you're going to prove that in this section, there will always be a positive gradient. How do you prove that along this section, there will always be a positive gradient mathematically? Well, by taking the following approach. Well, like I said here, the only way that we can show that this situation will always occur is to prove that the gradient of the graph in this section here is always positive. So now, just to clarify this important point a bit more clearly, as you know, when you've got a line that goes up, it's got a positive gradient. And if that's x1, and it's x2, then if that's x1, that will be corresponding gx1. And if that's x2, that will be the corresponding gx2. And you can see that in such a situation, gx1 will be always less than gx2. Why? Because the line's got a positive gradient. On the other hand, if the line's got a negative gradient, then if that's x1 less than x2, then you can see that if that's x1, that's going to be gx1. If that's x2, that's going to be gx2. So you can see in this particular case that gx2 will be less than gx1. And that occurs when there's a negative gradient in regards to line. So really, the only way that we can have a situation where x1 is less than x2 and that gx1 is less than gx2 is to have a situation where the line will have a positive gradient. And that's what I say down here. Then the only way that we can have x1 less than x2 and gx1 less than gx2 is for the line to have a positive gradient. Now, that is, we need to show that in this section, x1, x2, the gradient of the graph fx is always positive. That is, we need to show mathematically that in this section of the graph, the derivative is always positive. That is, we're going to show that dy dx is always greater than 0. How do you show that? Well, gx is equal to kx plus 1 on x plus k. Find g dash x. If we find g dash x by using the derivative function on the CAS calculator, TI Inspire, by typing g equal to kx plus 1 on x plus k, we will obtain g dash equal to kx plus 1 on x plus k all squared. But the thing is this, that g dash x will be wrong. Why? This is the incorrect derivative. The way we obtain the correct derivative is to again use the derivative function on the CAS calculator, TI Inspire, and type in gx equals k times x plus 1 on x plus k. And we will obtain g dash x equals k squared minus 1 on x plus k all squared. This is the correct derivative. All right. So please be careful when you are working out the derivative on the CAS calculator. If you got something like a constant k times a variable x, please put a times between the k and x, or else the CAS calculator would treat k and x as if it's one variable. So please jot that down. Please put a times between k and x. And I think that's one reason why a number of students didn't do too well in this exam question. All right. So yes, the correct g dash x is k squared minus 1 on x plus k squared. Now, so let's now investigate this derivative g dash x. Now, we know that the graph for gx equal to kx plus 1 on x plus k looks like that, where, like the question says, x is between negative k and infinity, and where k is greater than 1. Now, like I say here, clearly by looking at this graph, in the region where x is between negative k and infinity, the gradient of this graph is always positive. But the question wants us to prove this mathematically. By proving mathematically that g dash x is always positive. The way we show this is explained in the following manner. The derivative obtained by the TI Inspire CAS calculator was, like we saw before, g dash x equals k squared minus 1 on x plus k all squared. From the above graph, we can see that x will never equal negative k because it's a very good asymptote there. So as a result, when you think about it, x will never equal negative k. So when you think about it, x plus k all squared will never equal 0. And because when you square something, it always goes to the positive, then we can conclude that x plus k squared will always be positive. Therefore, we have the following. We have g dash x equal to k squared minus 1 on x plus k all squared. And we now know that x plus k will always be positive. And we get g dash x equal to k squared minus 1, and the denominator will always be positive. So therefore, when you think about it, in the final analysis, the thing that, because the bottom bit is positive, then when you think about it, in the final analysis, the thing that determines whether g dash x will be positive or negative will be the top bit, the numerator. In the final analysis, as I say here, the thing that determines the sign of g dash x will be k squared minus 1. Now, so we're going to investigate k squared minus 1. Now, therefore, let's investigate k squared minus 1. The question says k is greater than 1. Therefore, if k is greater than 1, then when you think about it, k squared minus 1 will also be greater than 0. So that is, k squared minus 1 will always be positive. And as a result, if k squared minus 1 will always be positive, then g dash x overall will always be positive. And as a result, we have proven mathematically that when x1 is less than x2, then gx1 is less than gx2. Now we go to the next question, which is question 4e. Now, 4e says the following. Question 4e, part 1. Let x be the point of intersection of the graphs of y equal to gx and y equals negative x. Find the coordinates of x in terms of k. All right. Well, on this page here, page 18 of these worked out solutions, what I've done is I've drawn the general G graph here with vertical asymptotes at negative k and horizontal asymptotes at y to k. And I've drawn, as stated by the question, the green line y equals negative x. Now, what do they say? The question says, let that point x be the point of intersection of the graph y equals g, which is that black curve there, and the green line y equals negative x. Find the coordinates of x in terms of k. How do you do it? Well, like you should know, to find the intersection between two curves, you've got to equate them. So therefore, gx curve equals negative x. What's gx? Like they say in the question, it's kx plus 1 on x plus k. And that's equal to negative x. Then you can find x in terms of k by using the solve function on the CAS calculator. And when you do that, you're going to end up with x equals negative k plus square root of k squared minus 1. So we now know that x. We now know that the x coordinate here. So we now know that the x coordinate of the intersection point is negative k plus square root of k squared minus 1. At which point we're going to find the corresponding y coordinate of that intersection point there by putting x equals negative k plus square root of k squared minus 1 into the line y equals negative x, because that's the quickest way of getting the answer. And that's what I've done on the next page here of the worked out solutions. So y equals negative. Every time there's a negative, please form the habit of putting in the brackets so to reduce the chance of making an error. And x, like we just saw, was equal to negative k plus square root of k squared minus 1, close brackets. And therefore, if negative times everything inside the brackets, we get to the k minus square root of k squared minus 1. So therefore, the coordinates of x shown in above graph are negative k plus square root of k squared minus 1, comma, y on it is k minus square root of k squared minus 1. So question 4e part 2 has been done. Question 4e part 1 has been done. Now we move on to question 4e part 2. Now, question 4e part 2. Find the value of k for which the coordinates of x are negative a half, a half. Well, all you're going to do is you just have to put the x coordinate of the intersection point negative k. You can put the x coordinate negative k plus square root of k squared minus 1 equal negative k, and use the solve function on the calculator to find k, or like a lot of us would do, and like I did here, you can use the y on it, which is all positive, which is great. So less negative, less confusing potentially. So k minus square root of k squared minus 1 is equal to a half. Find k using the solve function on the calculator, and k equals 5 on 4. So question 4e part 2 has been done. Now we move on to the next question. The next question is 4e part 3. Let z negative 1, negative 1, y 1, 1, and x be the vertices of the triangle xyz. Let sk be the square of the area of triangle xyz. Find the values of k such that sk is greater than or equal to 1. How do you do such a question? Well, let's sort of get the question a bit better in our minds by rereading the question again. What I've done here is, that's a photocopy of the exam question diagram. That's the general G curve. That's the line y equals x. And that's the point x that we saw earlier on. And that's a point z, the intersection point between the curve and the line. And that's a point y, the intersection point between the curve and the line. When you draw a triangle between y, x, z, you get this orange colored triangle here. Now, what is the question saying? The question is saying this: let z, which has got coordinates negative 1, negative 1, negative 1, negative 1, y, which has got coordinates of 1, 1, and x, and the coordinates of x we just saw were negative k plus square root of k squared minus 1 and k minus square root of k squared minus 1 be the vertices of the triangle x, y, z. Let sk be the square of the area of triangle x, y, z. Find the values of k such that sk is greater than or equal to 1. Well, they tell us in the question that the area of the orange shaded triangle xyz is of course that orange area there. They tell us in the question that the area of triangle xyz all squared equals sk. From that, they want us to find k so that sk is greater than or equal to 1. How do you do it? How do you do it? How do you do it? Well, find the area of triangle XYZ. first find the distance. First find the distance y. First find the distance YZ. How do you do it? Well, how do you find the distance YZ? Well, you've got to realise that that point Z is at x equals 1, and that point Y is at x equals 1. So what's the horizontal distance between x equals 1 to x equals 1? It's 2. So we now know that distance there, which is 2. Also, we know that the y-unit of Z is y equals 1, and the y-unit of 1, and the y-unit of point Y is y equal to 1. So what's the vertical distance from y equals -1 to y equals 1? It is 2. So now we know that that distance there is 2. Hey, that green triangle is a right-angled triangle. And because that green triangle is a right-angled triangle, then we can work out the hypotenuse of that green line, which is the distance from y to z, using Pythagoras' theorem. So using Pythagoras' theorem, which is a squared plus b squared equals hypotenuse squared, we get 2 squared plus 2 squared is equal to the distance yz, or squared, and that gets it to 8 equals distance of yz, or squared. When you square root both sides, you end up with distance of yz is equal to 2 square root of 2. So now we know that the distance from y to z is 2 square root of 2. Now, at which point we got to now find the distance from x to O. That is, we've got to find the distance from x to the origin. Well, we know that if we look at that blue triangle here, we can see that that blue triangle there has got a right angle. So therefore, we also know that that intersection point x that we saw earlier on has got coordinates -k plus square root of k squared minus 1 and y-unit of k minus square root of k squared minus 1. So therefore, we can work out the distance from x to 0 by using the fact that that blue triangle is a right angle blue triangle, and by using the fact that we can work out that hypotenuse of the blue triangle by using Pythagoras' theorem. So therefore, using Pythagoras' theorem on that right angle blue shaded triangle, which is a squared plus b squared equals h squared, we get, what's the distance from here to here? It will be equal to, when you think about it, k minus square root of k squared minus 1, or squared. And what's the distance from here to here? It will be k minus square root of k squared minus 1, or squared. All right. So be careful about this part here. Yes, the x unit here is -k plus square root of k squared minus 1, but to work out the actual distance from here to here, you've got to take out the negative. And when you take out the negative, it becomes negative brackets k minus square root of k squared minus 1. And therefore, the distance from here to here is k minus square root of k squared minus 1. It's just like saying, for example, that if, for example, this x unit was -3, the distance from here to here will be obtained by dropping off the negative, by removing the negative, which is 3. That's why we've got to remove the negative here. So to work out the distance from here to here in terms of k. Then that's equal to the hypotenuse of the blue triangle, which is distance xo squared. Now, at which point, because that's the same as that, you can put them together, it comes out to 2. It comes out to 2 brackets k minus square root of k squared minus 1 or squared equals distance xo. Then you square root both sides, and you get that the distance of xo is equal to square root of 2 brackets k minus square root of k squared minus 1. So now we know the distance of xo in this question. Now, at which point we can put all of the above together, and we get this diagram here on page 23 of my worked out solutions. We know from our recent calculations that the distance from y to z is equal to 2 root 2. And we know also from our recent calculations that the distance from x to o is square root of 2 open brackets k minus square root of k squared minus 1. So the original question was, find the area of the orange shaded triangle. Well, like you should know, one way to find the area of a triangle is to use area of triangle equals a half base times height. Do we know the base of this orange triangle? Yes, we do. It's 2 square root of 2. Do we know the right angle height of this orange triangle? Yes, we know. Yes, we do. It's square root of 2 brackets k minus k squared minus 1. So therefore, we can work out the area of that orange triangle by using area of triangle is equal to a half base times height, and area of triangle XYZ is equal to a half times the base, which is 2 square root 2, times the right angle height, which is square root 2 open brackets k minus square root of k squared minus 1, and that simplifies to a half times 2, it's 1, forget about it. Square root of 2 times square root of 2 is 2, and k minus k squared minus 1. And that's the area of triangle XYZ. But they do tell us in the question that SK is equal to the square of the area of that orange shaded triangle. So therefore, to get SK, you've got to square both sides, and you get SK equals 2 squared is 4, and it's k minus k or squared or square rooted squared there. Now, then from that, find k so that SK is greater than or equal to 1. That is, find k for 4 open brackets k minus square root of k squared minus 1 or squared greater than or equal to 1. Now, when you do that, when you find k so that for k minus square root of k squared minus 1 or squared is greater than or equal to 1, on the CAS calculator, you will get that k is between 1 and 5 on 4. That is 1 less than k less than or equal to 5 on 4. And that is the answer to that sub-question there. Now we move on to the next question, which is question 4F. What is question 4F about? Now, for F says the following. The graph of G and the line y equals x enclose the region of the plane. The region is shown shaded in the diagram. The graph G has what we've been seeing is that, and the line y equals x is that. Let AK be the rule of the function A that gives the area of this enclosed region. The domain of A is between 1 and infinity. Give the rule for AK. Okay, well, we know from the question that that's the general G curve that we've been dealing with, whose equation is kx plus 1 on x plus k. And also we got the line y equals x, which is also a line that we've been dealing with throughout this question. From the earlier calculation, we saw that point Z had coordinates of -1, -1, and point Y had coordinates of 1, 1. Now, we know from question 4E part 3 that x is between -k and infinity and k is greater than 1. Now, they tell us in the question about that shaded area there between the curve and the line, which are represented here as a pink highlighted area. So they want us to find basically that pink highlighted area. Well, AK is equal to the area of the pink highlighted region. The domain of AK, like they say in the question, is between 1 and infinity. Well, you can find that pink highlighted area by using integration, which says the area of the pink area is equal to the area between the two curves, which is equal to the integral of the top curve minus the bottom curve. And that will result to the following. It's the integral of the top curve, which is G curve, which is kx plus 1 on x plus k, minus the bottom curve, which is y equals x. Now, and we know that that intersection point there, which is the lower terminal, is x equals -1. And we know that that point there, which is the upper terminal, is x equals 1. Now, then, using integration function on the CAS calculator, what do we get? We get the following. We will get the following. That the area of the pink shaded area is equal to k squared minus 1 log e k minus 1 on k plus 1 plus 2k. And as a result, we have answered question 4F part 1. Now we move on to question 4F part 2. Now, what is 4F part 2 about? For 4F part 2 deals with the following. Show that the area AK, which is what we've just worked out, is between 0 and 2 for all k greater than 1. I repeat, show that the area K is between 0 and 2 for all k greater than 1. How do you show that? Well, I rephotocopied the diagram that we saw above, which is shown here. Now, the area AK, which is the area that we have just worked out, is this pink shaded area there. Now, and we know from our previous question that the gradient of G will always be positive. Okay. Therefore, the following won't happen. Because we know from a previous question, that the gradient of G in this region is always positive, then that won't happen. That little confusion won't happen. That the G curve will go down. Because if the G curve goes down, it's going to be a negative gradient, and that could create complications. And you get that secondary negative area there. But because we know from one of the previous questions with certainty that the gradient of G will always be positive, then that won't happen. The thing that will happen will be just that. That the G curve, like I say here, that the G curve will always be above y equals x. As a result, the pink highlighted area will always be greater than 0. That is, the area K will always be greater than 0. So we've answered part of the question. Now we move on to the next bit in this sub-question here. Next bit is this. I again re-photocopied the same diagram here. We know that intersection point there is at x equals 1, and that intersection point is at x equals 1. So what's the horizontal distance between x equals 1 to x equals 1? It's 2, as shown here. Now we also know that intersection point there is at y equals 1, and from previous calculations we know that y coordinate at point Z is at y negative 1. What's the vertical distance from y equals negative 1 to y equals 1? It's 2, as shown there. So we get like a sort of like a triangle here, sort of. Okay, we get sort of like a triangle that we can call YTZ. And within this triangle here, YTZ, we got the pink shaded area, as you can see. So that pink shaded area, when you think about it, will always be enclosed within that triangle YTZ. From that, we can say the following. From above graph, we can see that the pink shaded area is from the above graph, as what we just said, we can see that the pink shaded area will always be less than the area of the triangle TYZ. So as a result, pink highlighted area is less than the area of the triangle TYZ. What's the area of triangle TYZ? Well, you can work out the area of triangle TYZ by using area of a triangle equals a half base times height, and therefore a half times the base of the triangle TYZ is 2 times the vertical height of the triangle TYZ is 2. So therefore, what's a half times 2? It is 1. 1 times 2 is 2. So therefore, we have proven here mathematically that it is always the case, the way the question is set up here, that the pink highlighted area will be less than 2. That is, the area of the pink highlighted region is less than 2. Therefore, by putting together all of the above, we have the following. That we have shown that the area of the pink shaded area will always be greater than 0, which is shown here on this AK number line. And we have also just shown that the area K, that is the pink shade area, will be always less than 2, which shown on this AK number line will be all this region here, less than 2. So therefore, what's the common area between the top layer and the bottom layer? It is the area or the region between here and here, which is area AK will be always between 0 and 2. So we have proven mathematically that that AK will always be between 0 and 2. That is, 0 is less than area K less than 2. And by doing that, we finished that question there, and we have finished the whole of question 4.